I'm Chang from Peking University, Beijing, China. My presentation title is Robust Extreme Multi-Level Learning. Yeah, it's natural for an article or image to require multiple labels. For example, this image has the label people, fish, ocean, water, and this is another example. Almost any real world article or image needs multiple labels. For the complicated world, extremely large numbers of labels are inevitable. For example, Wikipedia has over 1 million labels for billions of people, each has a name. So extreme multi-label learning refers to working on an extremely large number of labels. This is the example of Wiki. Until now, the typical extreme multi-label learning methods are to build a classifier to annotate a new article or image with a subset of the most relevant labels. Typically, there are two categories. One is the tree-based algorithm, and the other is the embedding-based algorithm. The tree-based algorithm, including the fast XML, fast extreme multi-label, a tree-based classification directly optimized an NDCG-based ranking loss. And LPSR is another tree-based method. Another kind of method is the embedding-based method. Thus, exploit label correlation and sparsity to compress the number of labels. The typical method is SLEEK, a sparsely local embedding for extreme classification, a nonlinear local distance perceiving embedding based on KN. Another method is LEML, low-rank empirical risk minimization for multi-label learning. Assuming that the training label matrix is low-rank, low-dimensional embedding is found through a linear projection. Where on the large data sets, LEML appears inferior to SLEEK and FastML. For example, this the Amazon data set. The blue one is the LEML. The low rank assumption is violated by tail label. The tail label means that each label is assigned to at most 5 samples. This is the histogram of the label. And we can see a long tail. Over 100,000 tail labels in Amazon dataset. So it's hard to approximate with linear transformation. To solve the problem, we propose a robust extreme multi-label learning. We split the label matrix into 2 parts, a low-rank part and a sparse part. Y is label matrix, and YL is the predicted label matrix, and the YS is the predicted tail label matrix. Here's the objective. To minimize this objective, and we use XW to approximate YL and use XH approximate YS. So we get this transformed objective. To solve the problem, we further factorize the W into 2 parts, U and V, and we use L1 norm of xh to get the sparsity. The resulting optimization function is formulated as follows. For simplicity, we split the objective into 3 sub-problems and to solve them alternately, VUH. To optimize V, since each column of V can be independently updated, so it's easy to get a closed form of a solution by setting the gradient to 0. And since the dimension of Vg is generally small, to optimize U, which is also we can use the column to get a closed form. But due to the D is very large, so the matrix computation is very expensive. So the conjugate gradient descent method is more efficient. To optimize H, because LE norm makes the function not smooth, so it's challenging work. So we add 2 auxiliary variables, Z and mu, Z to replace the XHH. So we get three sub problem. To further improve our algorithm, the scalability, we use the divide and conquer optimization method. Divide Y into submatrix and solve each sub-problem in parallel, and combine submatrix estimates to recover the final solution using column projection. And we also discuss the generalization error. The population risk of the predictor error is not larger than the empirical risk of the predictor plus epsilon. And we also give Redmark complexity. And from this function, we can get by separating the influence of tail labels, the rank of W will be small. And the influence of tail label can be decreased by constraining the sparsity of XH. We conduct experiments on 6 data sets. The first 3 data sets are relatively small, and the last 3 ones are larger. And we can see the Amazon data set, the number of labels is larger than the number of features. And we compare our methods with a comparison algorithm. And we use evaluation matrix, 2 evaluation matrices, precision at K and NDCG at K. This is the results on 3 small data sets. The first one is our methods, and the third one is the LEML, the low rank method is our baseline method. And these are the results on 3 large data sets. First one is on the wiki10, and the second is delicious error, and the third is on the Amazon data set. And we can see the red one is our methods, and the blue one is the LEML. The green one is the sleek. Sleek is the nonlinear method. Our method is a linear method. And from the 3 histogram of this set, we can see the wiki10 and Amazon has a long tail, while the delicious has a short tail. So the LEML performs the worst on wiki10 and Amazon. We also evaluate the divide and conquer methods, and we divide y label matrix into 2, 5, 8, and 10 parts. And we can notice that the performance gradually decreases for large subproblem number. The optimization time cost can be decreased. And we can flexibly manage the optimization accuracy and the time cost. Finally, we summarize our methods. First, we develop a new extreme multi-label learning algorithm combining low rank and sparsity. And we treat tail labels with the sparse model, while usual labels with the low rank model. And we also apply divide and concur approach to improve the scalability and balance the accuracy and the computation. Yeah, thank you.
So we have plenty of time for questions.
Thank you. I wonder if you checked if your method, the accuracy of your method is dependent on where you put the threshold between the tail and the head of the distribution. I mean, the distribution is typically a long tail, a power law, so it's scale-free. It's just, somehow it's difficult to decide in a unique way where the tails begin. And I wonder whether this could somehow affect your method.
Yeah, we define the tail label is at the most 5 points, 5 samples for each label. So this label is with less samples. And we treat the tail label with the sparse model. We add a sparse model to treat it.
Okay. So in your algorithm, there are quite a few parameters, especially the low rank parameter and the. So how do you choose the dimension or the rank of the low rank label matrix?
Okay. Yes, it's by the experiment to choose one experience value. For example, we use the 200 or 500 or 300. Okay, I try this. Yeah.
Okay. So any other questions? So if there's no questions, let's thank the speaker again.